All right, welcome to section 7.2, where we're going to be solving exponential equations using logarithms. So in this box is a summary of all of the important stuff that you need to know about logarithms from section 7.1. If you haven't done some 7.1 homework yet, you might want to get some practice using these things, because we are going to be using all of this stuff a lot here. So let's look at example 1. Let's start right off here. To estimate the solution of 3 to the power x equals 4,000 two ways. We're going to do this the way you can solve any equation, get a solution of any old equation, by graphing first. But then the main idea of the section is the fact that you can use a logarithm as an operation that you can do to both sides of an equation. And we're going to see how that works in a moment. But first, let's solve this by graphing. We want to graph y equals 3 to the power x. And we also want to graph y equals 4,000. And see where these intersect here. I have this zoomed out from making a different video, so we're going to zoom back in until we can see where y is equal to 4,000 here. Okay, it's over here at this point. Click on it to get that intersection. Yeah, it looks like 7.55 is the solution. So if you do 3 to the power 7.55, you'll get about 4,000. And that's an approximation. It's probably not exactly 7.55. In fact, if you take your calculator and you do 3 to the power 7.55, you'll get 4,001.89. So it's an approximate solution, but it's close enough. Okay, so now let's plug in both sides of the equation into logarithm. So this is the main idea of the section. So you know that you can add a number to both sides of an equation. You can square both sides of an equation, take a square root of both sides of an equation, or divide both sides of an equation by something. A logarithm is another thing that you can do to both sides of an equation. So if you want to make 3x equal to 4,000 is the goal of solving an equation, if that's true, then log of 3x, 3 to the power x, should be equal to log of 4,000. So if you can make their logarithms equal, you'll make them equal to each other. But why does that help you? Like, why would I bother doing that? Well, let's look at the log laws. We have this b to the log of b to the power t equals t times log b. So you could write that exponent on the outside of the logarithm. So that's the trick here, is doing a logarithm of both sides allows you to write that exponent on the outside of the logarithm as multiplication by this number log of 3. And that multiplication now you can cancel out by dividing both sides by that number log of 3. And that just gives you x equals log of 4,000 divided by log of 3, which you can get with a calculator. Is about 7.549569, which is a bit more precise. If we do 3 to that power, we're going to get precisely 4,000. So I'm going to write it as 7.5496. All right, so that's the trick here, is that if you want to get an x, a variable, out of an exponent, you can take a logarithm of that and then use log law 3. That's what we're going to be doing for a lot of these problems here. So here's example 2, and this section is mostly solving a bunch of equations. Example 7, solving some more equations, and then you got some exercises to solve some equations. And this this method we're doing right here is going to be the most commonly used one. So let's try it with this one. We want to solve this equation. So you could take a log of both sides right now, but don't write this down because it's going to be kind of a little bit of a mess if you do this. If you do log of this, you can't just take the t over 12 out because you really have log of two things getting multiplied, and you'd have to use log law 1 first. And it would get a little bit ugly. So instead of doing that, I want to cancel out the 4,000 first. And that would give you 2 to the power t over 12 equals 7,000 divided by 4,000 is the same as 7 over 4. And now that you have it as just a 2 to a power equals 7 over 4, now is when you can do a logarithm of both sides. And it will work out nicely. Okay, so I'm doing log of both sides. Now, for this one, log law 3 applies. We have log of something to a power. The power is where the variable is, and the whole point of doing this logarithm is to use log law 3 and write that on the outside as t over 12 times log of 2. And running out of room here. You now want to get t by itself. You could divide both sides by log 2. And that would give you just t over 12 equals log of 7/4 divided by log of 2, and then if you multiply both sides by 12, you'll get t equals this whole thing, 12 times log of 7 over 4 divided by log of 2. And you might be wondering, why didn't I just actually calculate log of 7 over 4 back here, and also calculate log of 2, and then just deal with those decimals? I'll show you why here, because if you do them separately, this is what might happen. Well, you might do 7,000 divided by 4,000 first. And you get 1.75, okay. And then if you do log of that, you'll get 0.24. And a lot of students have a tendency to just like to round to 2 decimal places, so you might round it to 0.24. And then you get log of 2, you get 0.30 if you round that to 2 decimal places. And then when you do the log of 7 over 4 divided by log of 2, you might write that as 0.24 divided by 0.30, and then multiply that by 12, and you'll get 9.6. So if you do all these operations separately and then round things off as you go, you'll get 9.6. If you do it all at once, which is what I'm sort of recommending here. One big fraction with the numerator, which is 12 times log of 7/4. The bottom is log of 2. So we got the whole thing written in there. You get something a lot more precise, 9.688. And if you were doing this on Wiley Plus and it asked you to round your answer to one decimal place, and you wrote 9.6 here, it might mark you wrong. It's more like 9.7. So what happens, the reason this came out differently is because all of the rounding off you did along the way, every one of these steps here, you were rounding off. Like when you got the log of 1.75 and you just call it 0.24. And then you do more math, more arithmetic with that rounded off answer, your answer ends up getting off by a little bit more every time you do more arithmetic with a rounded off answer. So that's why I say don't round off until the end. Just leave it like that. And that's what I'm going to keep doing here. So let's see. Example 3. Katie invests $1,200 at 5.1% interest in a retirement fund, and at the same time, John invests $2,500 at 4.4%. When do their investments have the same value? So, if they retire at the same time, whose investment is worth more at retirement? Okay, so first, let's write a formula for the values of their investments after t years. So let's say K of t is the value of Katie's investment. Get it? KT? Katie? KT? Okay, anyways, it starts at $1,200. And it has a 5.1% interest. So we're going to use the formula 1 plus r to the power t, where the r is the interest rate, which if you write it as a decimal is 0.051. So in other words, that's going to be 1,200 times 1.051 to the power t. Now, John's is J of t starts at 2,500 and is 1 plus 0.044 to the power t. So you could write that as 2,500 times 1.044 to the t. Now what we want to know is when do their investments have the same value? So that means what is the value of t, the number of years, that makes these results be the same? So the same value means this equals this. So the equation that we're solving is going to be 1,200 times 1.051 to the t equals 2,500 times 1.044 to the t. Now, let's see. We want to get everything with a t on one side. So let's say we divide both sides by 1.044 to the t. Well, if you have these two things divided by each other and they're both raised to the power t, you can combine that into 1,200 times 1.051 divided by 1.044 to the power t. And over here we just have the 2,500. And I'm not going to divide this yet and just write it as a decimal because that would involve some round off error. And I want to save all of the calculations to the end, try to do it all in one step to minimize the amount of round-off error that you get when you use rounded-off numbers in more and more calculations. So, anyways, I'm going to divide by 1200 now to get that on both sides. And 2500 divided by 1200 is also known as 25 over 12. So what we have is 1.051 over 1.044 all to the power t equals 25 twelfths. And you want to get this exponent t out of the exponent. You want to bring it down. And the way to do that is to do a log of both sides of this equation. Log of the left side and a log of the right side. Log law 3 says that the t can come down, and you can just write it as 3 times log of this fraction. No, 3. What am I talking about? T. And that should be equal to log of this fraction. All right, now you want to get the t by itself, divide both sides by this logarithm. Because right now you just have multiplication, so you can just divide by this messy number. Should have left more room for this problem here. And you're going to get t is all of this after it cancels out on one side. And now I'm going to plug it all into the calculator. Log of 25 over 12 divided by log of 1.051 divided by 1.044. And we get 109.83. So what does this mean? That's how many years to be the same value. So yeah, Katie's is making a little bit more interest than John's, but John started with more than twice as much, and then is going up by 4.4% interest. So if Katie and John work for 120 years, then Katie will have more money in the retirement fund. But if they work for less than 109 years, Katie will have less money. So So I think it's pretty safe to say that unless they live to be 130 years old or something, that Katie will have less money. So John will have more. John is the answer to that question. Okay. That's a tricky problem. We'll do some more tricky problems in the next video. See you then.